All right, so next we're going to look into these spreadsheet examples of how to handle a couple of other problems, and I'm going to start here with these inventory management problems. Now, in Lab 2, you're going to deal with a muffin baking simulation, which is effectively an inventory management problem. And inventory management problems look a little different than a lot of the problems we've seen so far. The problems we've seen so far, you've had one arrival that will happen, but it will happen with a random time between it and the previous arrival and the next arrival. So the randomness is in the spacing of single arrivals. In inventory management problems, then typically we have regular non-random intervals. So think of a business. A business, you could model a business as if I'm modeling the long-term operations of a business, one way I could model it is thinking about how long between customer one's arrival and customer two's arrival, but that ends up being kind of cumbersome, and it seems a little silly to think about that there's like a lot of information there that you don't really need, when at the end of the day, so to speak, all you really care about is how many things did I sell. So rather than modeling the delay between the activity of inter-arrivals of customers, what we say is, well, we're actually going to model the day-to-day operations and then ask what happened per day. So each day, how many refrigerators did I sell? Each hour, how many newspapers did I sell? And so on and so forth. And so the inter-arrival times, well, they're evenly spaced, and we actually don't even really care about the inter-arrival times so much. But what we do care about is what is the random activity during the interval. So that's what I'm saying here, is that rather than drawing a time, we're going to draw a quantity demanded randomly at every regular interval. So in Lab 2, there'll be this muffin baking simulation. So you can imagine in a muffin baking oven, you get orders for muffins that arrive every minute. You can say, all right, this minute, how many muffin orders did I get? Or how many muffins just arrived at the oven? I don't care what's generating them, but I know that sometimes they get made at a particular rate and other times they get made at another rate, and all I do is every minute I check to see, are there new muffins that I need to put in the oven? So it's the number of muffins that arrive every minute that is the random thing that's changing, not the inter-arrival between every individual muffin. So in this case, you could say, well, what's my inventory here? Well, your inventory is kind of like your oven space. And so you can say, like if you have space for 30 muffins, effectively that's like having a stock of 30 things that you can sell. And if 31 muffins arrive, then that means that you didn't have enough inventory. So there's going to be one muffin that's going to be left unfulfilled, just like a customer that arrives and is not able to buy the product that she wanted because you didn't keep enough of them in stock. So the arriving muffins is like a demand, and the actual space in the muffin oven is like an inventory. So there's other ways that we could formulate the muffin sim. So we could think of demand as, like I said, daily muffin orders, and again, inventory as is this sort of oven capacity. All right, so a more classic example than this muffin making is the so-called news vendor model, which also goes by names the single period model or the perishable model. And some of you may have heard about this in some of your other classes. It's sort of a common example to go to for these sorts of inventory management problems. So the key properties here are fixed prices, uncertain demand, and a perishable product. And so if I put that cast them in terms of newspapers, then I can think of every newspaper as a fixed price, but I have no idea how many newspapers people are going to want every day. But I do know that if I don't sell any newspapers at the end of the day, they're trash. So I have a perishable product. The newspapers that if I oversupply newspapers one day, then that's a major cost to me because there's no way that I can recoup that cost. So nobody's going to want to buy a day-old newspaper the next day. They're going to want a new newspaper. All right, so in the kind of 470 way to do this is to think about just the average profit that I would get from this process. And so you can think of what's the expected profit, Well, that's equivalent to saying the expected sale price times whatever's smaller, the inventory or the demand. And then I take that and I subtract off however much it took for me to buy the newspapers or print the newspapers times my inventory. So you can imagine it might cost me, 5 cents per newspaper to print them. And so if I'm a news vendor, I've got 100 newspapers. Well, you multiply that by 5 cents, and that's how much I've already just paid just to get the newspapers out there before anybody's bought them from me. And then I might be able to charge 25 cents, but I'm only going to get 25 cents for either the few number of newspapers people buy or my entire inventory. But those are my options. I can't ever sell more than my inventory, but my inventory limits how much of a sale I can make. But so I can't ever, so that puts a ceiling on how much money I could make. But but I can't just keep infinite inventories because the inventory is also very costly to me. So I can then take this expectation problem, and if I know the distribution of demand, so I know roughly how I have some distribution that on every day, sometimes people order these many papers, other times people order a different amount of papers, but if I have some distribution, then I can plug that into this expectation problem, and then I can mathematically maximize my average profit this way. But the issue is that maybe average profit isn't something that's a useful performance measure to me. And so the kind of 470 way to deal with this would be to just sort of worry about averages. And then what if about some cases that mathematically are much more difficult to handle? Like, let's say that the unsold inventory, those newspapers, retain some actual small value. Maybe I can resell them as packing material or something. It may not be the full 25 cents, but at least I could, even if I sell them for a penny, I still make up some of the 5 cents it's cost me to print them. So when you include that into there, where your unsold inventory can be resold, it just makes the math much more complicated. And that's why there's an argument for why you might want to study this in simulation. So what the book does is they add their own little complications to the news vendor problem in order to justify the kind of simulation. They say we have a fixed quantity Q, capital Q, of newspapers purchased for resale each day. And then I have a demand, D, that varies based on some probability distribution each day. And so, of course, if my demand is greater than my quantity, then I'm going to lose out, because I'm only going to be able to sell my quantity Q newspapers, even though people were willing to buy more. But if my demand is less than my quantity, then I've got too many newspapers and I'm going to pay too much cost. So the question I have is, how does the quantity Q affect my aggregated profit over 20 days? So I could take an expectation here. So what is the expected profit over 20 days? But what the simulation can do is actually give me a distribution of profit, not just the average. So here's a distribution that comes out of a simulation. So on the x-axis is the amount of profit I got over a 20-day period. And over on the y-axis, it's the occurrence. And so this is a histogram. And you get this kind of bell-shaped curve, which makes a little bit of sense if you think about kind of a central limit theorem explanation, because I'm summing profits over different days. And so anyways, you get something that looks kind of humpy like this. There's other reasons why we can reason why it would look kind of like humpy like this. But the point is, now that I have this distribution, there's all sorts of more interesting questions I can ask that were just not available to me if I only cared about the expectation. So I could say that, I might be able to say, what is the probability that I am not going to be able to make $185 at the end of 20 days. Like, maybe that's really my performance target. Like, as long as I make $185 after 20 days, I'm a success. Well, this distribution tells me that, most of my probability is going to be under $185. And so I'm not doing so well. So, but if you think about it, the expectation might have been like $140. So if I would have simply asked, what's the expectation of the profit I'm going to make in 20 days, then I get $140. If my target was 185, then that doesn't give me a lot of extra information about how often I actually, whether there will be any cases where I'll actually hit my target or not. It's just it tells me that I'm totally out of luck. Now, imagine it going the other way, which would be even worse. Like, let's say that that the target I have was, say, $130, and my average was up here at like 140 or 145, something like that. And I'm sorry, did I say that backwards? I mean, my target is like $130 and my average is like 145. Well, if I just look at averages, then I'd say, oh, 145, that's greater than 130. I'm definitely going to meet my target. But the variance is so large that the averages don't tell the whole story, and half of the time I'm probably going to be under my target. So that's why this distribution is a much more useful tool for judging performance than the averages. All right. The other kind of classic inventory management problem you'll see in the textbooks is the so-called order up to, or MN, inventory control problem. And the question here is a twofold question: is how often do I check my inventory, and what is my target inventory level to order up to? So the order up to level is M as in Mary, and the how often is the N as in Nancy. And so I've got a little sort of image from the book down here. This is, I think, for a refrigerator system. And so the idea is you have this factory, and the inventory reviewer comes every N as in Nancy days. And every N as in Nancy days, the inventory reviewer sees how much is currently in the inventory and orders enough, Q1, to bring things back up to M. So this decline here, those are orders. So in this inventory period, these are people ordering refrigerators. And sometimes the decline is shallow, sometimes it's steep, sometimes it's really shallow. We don't know what it's going to be. But after N days, we see where we are in the inventory, and we bring it back up to M. So in this particular case, we brought it back up to M, but then they bought so many of us that actually they went on back order. So that might mean the customer just went somewhere else, or that might mean they back ordered, but they may not want to come and buy from us again because they had to back order from us this one time. So back orders can be very costly, but so can holding on to all of this inventory. So how do we deal with that? So the question is, how do I adjust these two parameters? How often I check and how much I order up to. Checking a lot can be very costly because, well, for one, if I have to pay my inventory person every time they check, that's one thing. But beyond that, because I don't think that's modeled in this particular case, if I check very, very often so that I basically ride this M line, then I'm going to be keeping huge amounts of inventory when I don't need to. So sometimes it's valuable to have that extra inventory space that I can use for other things. All right, so the book example is refrigerator sales. Each N is in Nancy days. You order enough refrigerators to bring inventory back to M, as in Mary. Orders take several days to arrive, so the lead time, that's another random variable here. So it's not just how many refrigerators are ordered, but it's also how long does it take for the order to get back to us. So each day, customers order a random demand, a random quantity. Lack of inventory leads to back orders or lost sales, and having too much inventory can also be costly because we have to buy, you have to rent a space to hold all these refrigerators so that they're available for you. So how does this policy affect the frequency of back orders? And so that's what we will end up simulating inside one of these things. So that's another example of something that actually we can simulate inside a spreadsheet. And if you go to section 2.4 in your bank's book, you can see how they did that all inside a spreadsheet. So that's definitely something that we will see a very, very similar problem implemented in one of your labs in Arena for inventory management, asking almost the exact same questions. But you could also do this inside a spreadsheet, and that may be valuable because your manager can easily access it and play with the numbers themselves. But if you want to run like an optimizer, like a goal seek, and try to figure out what the best M and N is going to be, then maybe the spreadsheet isn't the best tool for doing that, but maybe Arena and OptQuest is. So that's an example of some other things you can do in a spreadsheet. All right, so before we go on to the Monte Carlo examples, then I want to pause here and again give you an opportunity to answer a couple of questions in Canvas about this material.